What if vector spaces worked over rings instead of fields? And what if functions could be linear in multiple variables at once? Let's explore modules and multilinear functions. To find the architectural origins of the determinant, we have to look past the standard rules of linear algebra. Our goal is to formalize how these operators function over commutative rings with identity. We will use the rigorous framework established by Hoffman and Kunze to guide this deduction. Generalizing from fields to rings is the necessary step to prove why the determinant is a mathematically unique construction. By stripping away our usual algebraic shortcuts, we reveal the specific properties that force the determinant into existence. We begin by generalizing the space itself. When we take a standard vector space V and replace its scalar field with a commutative ring with identity, K, we create a module. Unlike a field, a commutative ring, such as the set of integers, does not guarantee a multiplicative inverse for every non-zero element. This shift removes the ability to reliably divide by scalars, fundamentally changing how we handle equations. Traditional linear dependence relies on the ability to isolate a vector by dividing by its coefficient. In a module, this operation is generally invalid. Consequently, the fact that a set of vectors is linearly dependent does not imply that one is a linear combination of the others. We define a submodule as any subset of V that is closed under the ring's addition and scalar multiplication. However, because division is restricted, not all modules possess a basis. We reserve the term free module for the specific cases that do. When a module is spanned by a finite subset, it is finitely generated. We define its rank as the smallest number of elements required to span the space. Theorem 5 in the text proves that if a free K module has n generators, its rank is exactly n. By establishing the rank of a free module without the use of scalar division, we have a structural basis to build function spaces on top of the vectors. With the space defined, we shift our focus to the functions acting upon it, specifically those that are linear in multiple variables. An R-linear form is a function that maps R copies of a module into the scalar ring K. Multilinearity requires the function to be linear in each individual argument, while other arguments remain fixed. If we provide a linear combination to a single input slot, the function distributes across that specific term. This lets us handle complex inputs one variable at a time. Example 9 demonstrates this with bilinear forms, where an M by N matrix A maps two vectors to a scalar through the operation x transpose AY. In example 10, Hoffman and Kunze observe that if we treat an N by N matrix as a set of n row vectors, the determinant function satisfies the definition of an n-linear form. The set of all possible R-linear forms is denoted M sub R, which itself constitutes a K module. To build this function space, we use the tensor product.
The tensor product of functions L and M evaluated on vectors alpha and beta is simply the product of their individual scalar outputs. Theorem 6 describes the dimension of this new space. For a free module of rank n, the space of all R-linear forms is also a free module. Because of this multiplication of dimensions, the resulting rank of this massive new tensor space is exactly n to the power of r. We construct the basis for this space by taking all possible tensor products of the dual basis elements. While this n to the r space is comprehensive, its complexity is too high for geometric applications. We need a constraint to narrow our focus. We refine our function space by introducing the alternating constraint. An alternating form is defined by a single rule. If any two input vectors are equal, the output must be 0. This rule dictates how the function behaves when inputs are swapped. If we evaluate the form on the sum of two vectors, alpha plus beta, and expand it multilinearly, we generate 4 terms. Since identical inputs yield 0, the alpha-alpha and beta-beta terms vanish. Swapping two vectors flips the sign of the output. By extension, any permutation of the inputs multiplies the result by the sign of that permutation. We call the set of all such functions A sub r, the submodule of alternating R-linear forms. Theorem 7 establishes the rank of this specific space. In an alternating form, any basis element with repeated indices becomes 0. Furthermore, since swapping indices only changes the sign,
Every form is determined entirely by its values on basis sets where the indices are strictly increasing. The number of ways to choose such a set is n choose r. This means that if the number of inputs r exceeds the module's rank n, no such strictly increasing set exists, and the space of alternating forms collapses to 0. But when the number of inputs matches the rank of the module exactly, n choose n equals 1. This result proves there is only a single basis element for alternating n linear forms. Up to a scalar multiple, only one such function can exist. The determinant is the unique manifestation of this rank 1 alternating space. It is the specific function that satisfies these constraints, while assigning a value of 1 to the identity matrix. By generalizing from vector spaces to modules, we established a way to work without the convenience of scalar division. By extending linearity across multiple inputs, we mapped out the large function spaces governed by tensor products. Finally, the alternating property reduced that tensor space, revealing that for n inputs, only one unique linear relationship exists. These mechanics, modules, tensors, and alternating forms, are the structural requirements for exterior algebra and tensor calculus. Removing our algebraic assumptions reveals the underlying architecture of geometry, proving that the determinant is a necessary result of these first principles. If you found this helpful, like the video and subscribe for more clear explanations from Hoffman and Kunze linear algebra.